Hello everyone, welcome to another video on the Medidata's Perspective channel. In our today's video, I'll be walking you through how I went about predicting cardiovascular disease on this data set. This project is an actual project which I carried out for my school activity. So kindly stay tuned as I walk you through this project. Without wasting time, let's dive right in. The first thing I did was to import the libraries which I'll be needing. That's Pandas NumPy, Matplotlib and Seaborn. I went ahead to read in our dataset next. This dataset is an Excel file, so I used the pd.read_Excel to read in my file. After that, I did some brief changes to the dataset, just like for example, our gender column, we had 2 and 1, where 1 was for male and 2 was for female. I had to recode these columns to 0s and 1 using the np.where function. I passed in that my gender column and I identified that 1 should be encoded as 0 and any other value should then be 1. So you could see that the changes were effected after I printed out my data. The next thing I did also was to change my column names. For example, the AP_HI value was changed to our systolic blood pressure column, while the AP_LO column name was changed to our diastolic_BP column. I specified that these changes should be in place by using the inplace equals to true parameter. So if you look at our table here, you could see now that our changes were effected. We have systolic blood pressure and our diastolic blood pressure column. Another change I carried out was for the age column. So previously, if you look at our age column, you will see we have a whole lot of values and these values were in days. So to convert this to age, I had to divide by 365 days, which is in a year. And I used the np.round function, passing our age column, which we want to modify, divided by 365 days, which we have in a year, and with this I was able to get our age in years. If I scroll down, you see the new column which we created called the age_year, and now you can see our ages for each of these rows of data. Now after carrying out those cleaning activities, I used the .info method to view my data set, and with this I was able to find out that we did not have any missing values in this data set. I was also able to find out that we had 7,000 rows of data and 14 columns. I used the isNA.sum method once more, and with this you could see I could now confirm that we don't have any missing values. Now the next thing I did was to check the variance of our variables. Using the .var method, I was able to look at the variance of each of our columns, and with this we can see that a lot of our columns had high variance in their values. Now the next thing I went ahead to do was to prepare my data set for machine learning. Before I went ahead to do that, I wrote a brief write-up to say that logistic regression, support vector machine, random forest and gradient boosting will be used to evaluate on the classification performance. The models will then be combined to develop a weighted ensemble model capable of leveraging the performance of the disparate models to improve the detection accuracy. So to prepare my data set for machine learning, I first of all dropped columns that wasn't necessary for our machine learning. So I dropped the ID column, age column, and also our target variable, which is the cardio column. And I went ahead to save this as our S values, which is going to be our features. Then to get our target variable, all I had to do was to get the cardio columns from our data set once more and use the .values attribute to get only the values. I went ahead to call on the shape attribute on the S and Y variables to get the shape of our data set. With this, we can see we have 70,000 rows of data and 11 columns. Now, the next thing I did was to import the train test split method from sklearn.model_selection. Using the train test split method, I was able to split the X and Y variable and also set our test size to 30%. I ensured to set our random state to 21. Now the first machine learning model we'll be creating is the logistic regression model. For the logistic regression model, I stated that logistic regression model uses some form of distance to inform it. So for the above features, which are the explanatory variables, where there are features on larger scales, it can disproportionately influence the model. So for this reason, I was going to set the features to be on the same scale by standardizing. So to do this, I had to import the standard scalar from sklearn.preprocessing, import our logistic regression from sklearn.linear_model, and also import pipeline from sklearn.pipeline, and our accuracy score, recall score, F1 score, and precision score from the sklearn.metrics. I initiated the standard scalar and I set the variable as scalar. This variable, which is scalar, was then used to fit transform our S-train data. Remember that we got our S-train data from the train test split method. I also used the standard scalar to transform the S-test and save this as S_test_scaled. With this done, I created a list called steps, and this list contained our standard scalar, which was initiated, and also the logistic regression model. I passed this into the pipeline, and with this I was able to fit our training data by calling our pipeline on the S-train scaled and our Y-train data. To make prediction on the test data, I also used the pipeline to predict on the S-test scaled data. When I was done with this, I was now able to calculate and print out the accuracy score on our test data. I used the .score method on the S-test scaled and our Y-test data to print out the accuracy score. And also to print the recall score, I used the recall__ method on the Y-test and our Y-pred data. I did this for F1 score and the precision score also. So from this, we can see that our accuracy score on the test data was 72%, our precision score was 74%, while the recall score and F1 score was 67 and 70% respectively. The logistic regression model is used for classification problems, and if the probability is greater than 0.5, the data is labeled as 1, while if the probability is less than 0.5, that data is labeled as 0. So to create our logistic regression ROC curve, I had to call the predict_prober on our S_test_scaled data, and I went ahead to save this as the Y_pred_probes. With this, I was able to plot the ROC curve by importing ROC_curve from the sklearn.metrics. I passed our Y-test and our Y-pred probes to the ROC_curve function, and I plot this curve using these lines of code. So if you look at this line of code, you could see that I passed the false positive rate and the true positive rate to our plt.plot function, and with this I was able to create this line plot. An ROC curve shows the performance of a classification model at all classification threshold, and it can be used to evaluate the strength of a model. ROC curve can also be used to compare two models. A classifier that gives curves closer to the top left corner indicates a better performance, while the AUC represents the degree or measure of separability. It tells us how much the model is capable of distinguishing between classes. An AUC of 0.5 suggests no discrimination, while an AUC of 0.7 to 0.8 is considered acceptable. An AUC of 0.8 to 0.9 is considered excellent, and an AUC that is more than 0.9 is considered outstanding. So to calculate the ROC AUC score, we had to import the ROC_AUC_ from sklearn.metrics and pass in the Y-test and the Y_pred_probes. With this, we're able to get our logistic regression ROC AUC score, which was 0.78. And remember earlier I said an AUC score of 0.7 to 0.8 is considered acceptable. Although earlier on we've noticed that there's a huge difference between the variance in the different columns, from here henceforth I won't be standardizing or normalizing the variables, as I'll be using classification tree models because it has ability to describe non-linear dependencies and it does not require pre-processing of variables before modeling. So the first classification tree model I'll be using is the random forest classifier. The random forest classifier is an ensemble method and it uses a decision tree as a base estimator. The final prediction is made by majority voting. So to create this model, I had to first of all import our necessary libraries such as the random forest classifier from the Scikit-learn.ensemble and also accuracy underscore from our Scikit-learn.metrics. I went ahead to initialize the random forest classifier with the desired parameters such as our n underscore estimators as 100 and our mean underscore sample leaf as 0.12. I also set a random state to 21. After initializing our random forest classifier model, the next thing I did was to fit the classifier on the training data, which are the S train and Y train data. I went ahead to make prediction on the test data using the .predict method. Now to calculate and print the accuracy score, I use the accuracy score method which we've imported earlier, the recurse score method, F1 score method, and also the precision underscore method. So with this you can see we got 71% accuracy for our random forest classifier, 64% recurse score, 69% F1 score, and 75% precision score. I was also able to get the feature importances by using the feature underscore importances underscore. With this, I created a pandas series, passing the data columns as the index and sorting the values also so that we could get the most important features on top. So from this bar plot, we can see that our systolic blood pressure, diastolic blood pressure, and age are the most important feature for detecting if a patient is going to have cardiovascular disease or not. The next thing I did was to get the AUC score of our random forest classifier using the ROC underscore AUC underscore from the Scikit-learn.metrics. And with this you can see that our random forest classifier AUC score was 77%. The next classification tree model which I will be using is the gradient boosting. In gradient boosting, each predictor in the ensembler corrects its predecessor error, but the weight of training instances are not changed, rather each predecessor is trained using the residual error of each predecessor as labels. From the Scikit-learn.ensemble, I imported the gradient boosting classifier and we initiated our model and passed in our parameters such as the n underscore estimators, maximum depth, and our random states. We fit this our model, which is the GBT model, to our S train and our Y train data and call the GBT model to predict on the S test. Now the next thing I did was to calculate the accuracy score on our Y test and our Y predictions. We also calculated the recurse score, F1 score, and the precision score using the various libraries. So from this, we could see that our accuracy score for our GBT model was 72%, the recurse score was 64%, our F1 score was 70%, while the precision score was 76%. I also got the feature importances of our gradient boosting classifier, and the most important feature for prediction was the systolic blood pressure and age. Now the next thing I did was also to calculate the AUC score for our gradient boosting classifier, and with this I got an AUC score of 79%. Another machine learning model which I used was the support vector machine learning model. I imported SVM from Scikit-learn, imported the SVC from Scikit-learn.svm, and also imported accuracy underscore from Scikit-learn.metrics. I initiated the SVC classifier and set the parameter of probability to false. With this, I was able to fit our S train and our Y-train data. I use the decision underscore function method on our S-test to get the decision scores. Also, to get the AUC score, I imported ROC underscore AUC underscore score from the Scikit-learn.metrics, and I passed in our Y test and our Y decision scores data to the ROC underscore AUC underscore call method. I also made predictions on our S-test using the SVM underscore classifier model which we've initiated. I printed the SVM accuracy score, recall score, F1 score, and also the precision score. So with this, we're able to get an SVM accuracy score of 72%, a recall score of 62%, an F1 score of 69%, and a precision score of 77%. The AUC score for our SVM was 78%. To get our feature importances for the SVM classifier, I had to call on the .coif underscore to get our feature importances from the SVM model. And then I used the numpy.argsort method to sort our feature importances. To visualize these feature importances, I converted the feature importances list element to a numpy array, and I passed in the arrays to our pandas.series method. I called the sort underscore values on our importances, and with this I was able to create a bar plot. So if you look at our SVM important features for predicting patients with cardiovascular disease, you'll find out that cholesterol, and if a patient is active, and alcohol were the top features for predicting cardiovascular disease. The example learning is a solution that takes the advantages of CAT while reducing the ability to memorize noise. In example learning, different models are trained on the same dataset, and each model are allowed to make its prediction. The final predictions are more robust and less prone to errors. Now the next thing I will be doing is to create a voting classifier to get the best models from all the models which we've initiated and created. So to do that, I have to instantiate all the individuals classifiers which we've used. The first thing I did was to pass in our standard scalar and our logistic regression into a list and create a pipeline with this. Our random forest classifier, gradient boosting classifier, and the support vector classifier were all passed into a list and saved as classifiers. And with this, I was able to create a tuple containing our classifiers and our classifier's name. The next thing I did was to fit this classifier into our S-train and our Y-train data and predict on the S-test to get our Y predictions. I also got an accuracy score for each of these classifiers, and with this you could see our logistic regression accuracy score was 72%. The random forest classifier gave us an accuracy score of 71%. The gradient boosting classifier gave us an accuracy score of 72%, and the support vector machine classifier gave us an accuracy score of 72% also. The voting classifier is an example learning technique where different models are used for one training set. Now to use our voting classifier on our model, I had to instantiate the voting classifier first and set our parameter of estimator as our classifier. I fit this our VC, which is our voting classifier, to our S-train Y-train data, predict on our S-test to get our Y predictions, and with this we're able to evaluate the test data to get the accuracy score and print the recall score for our test data, the F1 score, and the precision score also. So for the voting classifier, the accuracy score was 72%, the recall score was 61%, the F1 score was 68%, and we got a precision score of 78%. So to calculate the combined feature importances from our voting classifier, we had to use the numpy.average and pass in a list containing the various feature importances of these various models. and print out the combined feature importances by calling the combined underscore. I created a bar plot using the combined underscore feature underscore importances variable which we've created by using the pandas.series method. I called the sort values method to sort these importances according to the most important, and with this we could see that our systolic blood pressure, cholesterol value and our diastolic blood pressure are the most important columns for predicting cardiovascular disease. I also went ahead to create a pandas data frame so that I can see all the metrics of the various models which we use at a glance. So with this I was able to get the accuracy score, precision score, recall score, F1 score and the AUC score on a table presentation where we can see the logistic regression, random forest classifier, gradient boosting classifier, SVM classifier and the example voting classifier. So with this I can see that the model with the best accuracy was the gradient boosting classifier which had an accuracy score of 72%, just like the logistic regression and the example voting classifier also. While for precision, the example voting classifier had the highest precision score. For recall, the logistic regression classifier had the highest recall score, while for F1 and AUC score, the logistic regression classifier and the gradient boosting classifier respectively had the highest scores. The next thing I did was to calculate the ROC curve and the ROC AUC for each of these models so that I was able to create an ROC curve for each of our models and compare. So this is the code I wrote to go about doing that, and with this line of code I was able to create this graph to show all our ROC curve for our various models. I ended this project by writing a brief summary of our background, the method I used, our results and conclusion. So for the background, I stated that cardiovascular disease is one of the main causes of death worldwide. Identifying and predicting the disease in patients is the first step towards stopping its progression. The capabilities of machine learning models in detecting at-risk patients using survey data was evaluated, and the key variables that contribute to this disease among patients was identified within the data. The method I used explored data-driven approach, which utilized the supervised machine learning models to identify patients with such disease. I conducted an exhaustive search of all available features variables within the data to develop models for cardiovascular detection. Different machine learning models such as the logistic regression, support vector machine, random forest classifier, and the gradient boosting were evaluated on their classification performance. The models were then combined to develop a weighted ensemble model capable of leveraging the performance of the disparate models to improve detection accuracy. Information gained of tree-based models was used to identify the key variables within the patient data that contributed to the detection of at-risk patients of the disease class by the data-learned models. For our results, the developed gradient boosting classifier model for cardiovascular disease achieved an area under receiver operating characteristics, which is the AUC ROC score of 79.6%. The top 5 predictors of the disease was cholesterol, activity, alcohol, glucose, smoking as key contributors. For my conclusion, I wrote that machine learning models based on the survey questionnaire datasets can provide an automated identification mechanism for patients at risk of cardiovascular disease. I also identify key contributors to the prediction which can further be explored. So this brings us to the end of this video. I hope you enjoyed this video and it was educative to you. For more content regarding healthcare data analysis and analyzing data science projects on healthcare, please subscribe to this YouTube channel. Also share these videos to your friends and loved ones that you know are interested in analyzing healthcare data. Leave a thumbs up if you like this video and remember to drop your comment and question in the comment section below. Bye for now and see you in my next video.